So we have seen the examples of the positive, how we pre-process the positive classes. Now we'll see how we pre-process the negative classes. So again, similarly, I've defined the path where the negative classes are kept. Now these are, as you remember, these are images with without potholes. So that's our negative images. So we have around 21 images with the negative classes. So this is something which we have seen earlier. The next process to extract the data. Now we are reading through each of those images, reading the image, reading that image, and then we are extracting two patches. If you remember, in the image pyramids, we extracted around 10 patches, but now here we are just extracting two patches of 128 into 128 from each of those images. Why it's only two patches is because to keep the ratio between the positive and negative classes to a more balanced thing. If we had more positive classes, we could have extracted more patches also. So for each of those patches, we are resizing it into a 224 into 224 because our initial patch size is only 128, so we are resizing into 224 into 224. And like earlier, we are converting into an array, pre-processing it, and then appending the data the data array into that list, and then the labels we are appending as 0 because this is the negative class. So totally we have around 73. So this is including the 31 which we had earlier, and 21 into 2, which is 42 plus 31, we have 73. So now we have the data and the labels as a list. Now what we will do is we'll just convert that into an array format, and then let's look at the overall shape of the data. So the shape is this, where 73 is the number of examples, and then 224 into 224 into 3, that's our dimensions. So that's the overall shape of it. Okay, next is to train any neural network, as you know, we need to convert the labels into a one hot encoded format. So that is what we are using the label binarizer here for. And we convert the labels, which is just ones and zeros, into a label into a one hot encoded format. Let's look at what this one hot encoded format is. So this is how the one hot encoded format is. The first axis is for the 0 class, or whichever is 0. So that is the first axis is for the negative classes, that this is not a pothole, and the second is for is a pothole. So whenever there is 1 here in the second axis, that means these are examples where it has a pothole, and whenever you have 1 in the first axis, that means these are examples where there are no potholes. So these are your negative examples where 1 is in the first axis, and the other one is the positive examples. And then we will split the data into train and test set using the train test split function, which is part of your scikit-learn. So let's look at the shape of the data. So our test size is only 15%. So we have 62 training sets and 11 test sets out of the 73. So this is how we split into train and test sets. Next, we will look at the transfer learning process. Now, having split our data into train and test set, now let's get into the details about transfer learning. So this is what we will do in the transfer learning process. So here MobileNet VNet is our base network. So this is where we downloaded, or we had imported that package called MobileNet VNet. This is part of TensorFlow itself, which supplies these different models for us to do transfer learning. So that is MobileNet VNet, which we will use for transfer nets. Now, so some of the basic parameters are weights. So here, this MobileNet has been trained using ImageNet data. Now, so that's why we are giving the weights as ImageNet. this is something which is important. Include top is called false. Now, what it means is, as we saw in the transfer learning, we are not using the top part of the network, which is basically the softmax layer, which is we take the after all the feature extractions, the last layer is the softmax layer, which is used for prediction. So we are excluding that top layer and only taking the other layers, which is already which is already optimized layer, and then we'll be using we will be building our own top layer on top of this, which we'll see earlier next. And then the input dimensions are 224 and 224. So if you remember, we had resized our images into the size, so that's why we are giving the input shape as 224 and 224. So that's the base network. So this is without the top, this is the base network. So the next line 4, which we are defining a top network, the top network as the base network dot output. So the output of this base network is we just naming it into a new variable called the top network. Now what are we going to do next is going to build another top layer. So as we have seen that we have excluded the original top layer of the base network, and then we are building a custom top layer on top of it. So these are the kind of layers which we are building it. We are building an average pooling layer with this pool size on this top network, which is the output of the base network, and then we are flattening it. So we are just just only doing an average pooling layer. Now what if you want, you can even add a CNN layer or any other layers which you want on top of it. So I'm just doing only a average pooling here, and then we are flattening it. So flattening is a process before we build a dense layer. So and then we build a dense layer on top of it. So dense layer, as you know, is a fully connected layer. So the dense layer is built and with an activation of relay activation. So as you see, top network. So you take this output and then feed it into this dense layer, and again you're doing a regularization, which is a dropout regularization again on the top layer, and the final layer, which again is a dense layer with a softmax activation. So the dimensions of 2 is because we have only 2 classes, the positive and negative classes. So that is why we have dimensions of 2. You can even add, if you want, you can experiment with different multiple layers here. Maybe multiple dense layers. Maybe you can start with 256 and then slowly reduce it to 128, and multiple layers. Only what you need to remember is always provide the output from each layer as an input to the next layer, like this. So I've taken only one dense layer, and the final dense layer is obviously your softmax layer. So and here is where we define the model. So our model is using a specific class called model. So this model is something which we have downloaded or imported here. So this is this model. So we are using that model class to build a model. And here, so the inputs to this layer is the base network's input. So here the whatever was the base network's input we have defined, that is our inputs, and the outputs is this top network. See, what we get out of it finally, which is your softmax layer, is your output. So when we define this model object, you have to define this input and output, and this is how we define it. So this is the most important or next thing which you have to note here. So here, as we said, in the warming up stage, as I explained earlier, in the warming up stage, we are going to freeze all those layers of this network. So here, and this is done using this for loop. For each layer of the base network layer, we are saying that it is not going to be trained. We are not going to train it. So we are only going to train this part, the custom layer which we have built. So that's all what we are going to train here. And the whatever was the older layer which was part of the mobile net architecture, we are going to freeze it. We are not going to train it. So that's what this says. So next, having seen this the base network, what we'll do is we'll go and train or train this this base network by after freezing the all the layers in the network. So that's what we'll see next.